so this talk is going to be mostly about trying to determine what the equation of state of neutron stars is using observations of binary neutron stars. So the main way so the equation of state of neutron stars for systems that are in binary systems is essentially a zero temperature equation of state. So the thermal energy in the neutron star is much less than the Fermi energy, and so you can essentially treat it as zero temperature. And so your equation of state is just a one-parameter equation where the pressure is a function of density. And this is fairly unknown. It's not known exactly what is inside a neutron star. There could be just standard neutrons, protons, electrons. There could be other things like strange quark matter or hyperons or mesons. But currently there's a lot of uncertainty, and the pressure is unknown to a factor of several, like a factor of 5 or so. And so that's what I'll be talking about, is trying to measure that. This is work I've done with Les Wade, who's a grad student at University of Wisconsin. So just to give a very brief overview, I'm sure everybody knows about gravitational-wave detectors. There's two in the US, LIGO. There's one in Italy called Virgo, one in Japan, which is currently being constructed, CaJAGWR, and then possibly another LIGO detector in India, if that gets finally approved. So these, they're now constructed. We should begin observing them later this year, and by the end of the decade is when they should reach design sensitivity. They're sensitive to a range of gravitational wave frequencies from about 10 hertz to a few kilohertz, which is where binary neutron stars merge. Okay, so I just want to show what the waveform of a binary neutron star system looks like. So it's typically, if you start around 30 hertz, it's about a minute long. You have a few thousand gravitational wave cycles. It starts, if you start around 30 hertz, which is where gravitational wave detectors are initially sensitive to. And what I'm showing you here are two waveforms. One is a binary black hole waveform, and one is a binary neutron star waveform of the exact same mass, of around 1.35 solar masses for each planet. If you look at the very beginning of the waveform, they're essentially identical. So for most of the inspiral, the waveform depends only on the masses of the system. You can essentially treat them as point particles. And this is, the masses are parameterized in terms of a chirp mass, which is one combination of the masses of the bodies, and a symmetric mass ratio. It isn't until you get to the very end of the inspiral, around 400 hertz, where you actually start to see a sizable difference between the binary black hole waveform in black and the binary neutron star waveform in green. And at this point, after around a couple thousand cycles, there's a phase difference of about 1 radian due to matter effects, which is mostly in the form of this tidal interaction that I'll talk about. Finally, after 400 hertz up to about merger, you have maybe 20 to 30 gravitational wave cycles, and the difference in phase between a binary black hole waveform and binary neutron star waveform starts to accumulate, and you can get a phase difference of around 1 gravitational wave cycle. And then finally, after merger, a lot more interesting things can happen. You can have either a front collapse to a black hole if the neutron star equation of state is soft, or if it's stiff enough to support a hypermassive remnant, you get these oscillations, and they're typically around a few kilohertz, and this depends very sensitively on the equation of state. So if this is measurable, that would also be another way of learning about the equation of state of neutron star matter. So what I'm showing you here is just the Fourier transform of the waveform plotted on top of the noise curve of several gravitational wave detectors. So this is the planned final sensitivity of Advanced LIGO. This is a binary neutron star system at about 100 megaparsecs. So most of the information about the masses of the systems comes at around a few tens of hertz to a few hundred hertz. And then it isn't until a couple hundred hertz where you learn about tidal effects. And then finally, after merger, there is these post-merger oscillations. However, the noise curve starts to go up dramatically, and so it's not clear that there will be any information from the post-merger stage. So what I'm going to talk about mostly is the tidal effects that you see from a couple hundred hertz all the way up to merger. So just to give a more technical description of how these tidal interactions work, so each neutron star creates a tidal field that can induce a quadrupole moment in the other star. So the quadrupole moment is Q, the tidal field from the other star is E, and the amount of deformation that you get depends on the equation of state, because the equation of state essentially determines what the radius of the neutron star will be. And so if you have a stiff equation of state, which means that there's a lot of pressure, then what happens is you have a large radius, and so there will be more distance over which the gravitational gradient from the other star can act, so you'll get more quadrupolar distortion. If you have a soft equation of state, then you end up with a small neutron star. It's more centrally compact, and you have a smaller distance over which the gravitational gradient can act. So you'll have a small quadrupolar distortion. And this is parameterized by this quantity called the tidal deformability, which is just the ratio of the induced quadrupole moment to the tidal field that created the quadrupole moment. And that depends on the equation of state and mass. And for a lot of this talk, I'll use this quantity capital lambda, which is just a dimensionless version where you divide by the total mass of the neutron, where the mass of the neutron star is. And so the way this affects the waveform is, what happens is this quadrupolar interaction increases the binding energy of the system. And you also, because there's an additional quadrupole moment, it adds to the total quadrupole moment of the system, so you get more gravitational radiation. So the system's more tightly bounded, it'll orbit around faster, and also it'll radiate gravitational waves, so it'll inspiral faster. And so that's what creates the phase shift in that gravitational waveform. So now I just want to give a brief overview of exactly how this affects the waveform. So I'll be talking about mostly post-Newtonian waveforms. So this is an expansion of the Einstein equations and powers of the speed of the bodies, and for bound systems, the compactness of the system. So this is expanded in powers of x, which is that right there. So what you do is the end result you get is essentially the energy of the system and the gravitational radiation luminosity of the system. This is the Newtonian potential here. And then the energy is currently known to fourth post-Newtonian order in powers of x. And then it isn't until the fifth post-Newtonian order where you start to see tidal effects. This is technically a Newtonian effect, so any set of bodies has a tidal interaction, such as the Earth and the Moon. However, it comes in at power x to the fifth, so it looks like a fifth post-Newtonian effect. And then it's also known to next to leading order, which would be a 6 p.m. effect. And the luminosity, this is the leading order contribution that you get from the quadrupole formula. Then it's also known to 3.5 post-Newtonian order. And then again, the luminosity is known to 5 and 6 p.m. order. So once you have expressions for the energy and luminosity, the way you find the phase of the waveform is by through the energy balance equation. So the rate of energy loss is equal to the negative of the luminosity. And so you can just rewrite that to get a set of ODEs for the changing x with respect to time and changing phase with respect to time, just using the expression for the post-Newtonian expansion parameter. And so there's several ways to integrate this system of equations. And this, because you have this freedom, you could end up with an uncertainty in what the true phase should be because of this freedom. So one way of doing that is just to numerically solve this set of equations. You could also re-expand this expression. That gives you a different result. You can do this analytically and then invert it to get a function, the waveform as a function of time, and the phase as a function of time. And then once you've done that, you can just plug this into the expression for the waveform phase. So what's usually used in data analysis is the frequency domain waveform. Most data analysis is done in the frequency domain. And so I'll just describe what the Fourier transform of the waveform looks like. So most of the extrinsic parameters about the binary system coming in the amplitude of the waveform. So this is the static position, the right extension declination, the polarization angle, and the inclination angle, and divided by the distance. And then most of the information about the intrinsic parameters, such as the masses and the tidal parameters that we'll care about, coming in the phase. And so the phase looks like this. So it depends on time and phase of coalescence, which are just two parameters. And then at Newtonian effect, we just measure the chirp mass of the system. And then at higher post-Newtonian orders, you can start to measure the symmetric mass ratio. And then at fifth post-Newtonian order is where you start to see the tidal effect. And the leading order contribution is this quantity lambda tilde, which is just a linear combination of the tidal parameters of the two neutron stars. And then at sixth post-Newtonian order, again, you see this quantity lambda tilde, and then there's a very small remainder term, this quantity delta lambda tilde, which again is just a linear combination of the two tidal parameters. And so this is a very small correction. It's about 1% as big as the main term lambda tilde. And for equal mass systems where eta is a quarter, it in fact just goes to 0. So it will turn out that the only thing we can measure are the two masses and then this quantity lambda tilde, and this quantity will be completely unmeasurable. Okay, so once we've seen several binary neutron star observations, we can try and stack them and try and measure the equation of state instead of the tidal parameters. So it's well known that if you, for example, know the radius as a function of mass or the tidal parameter as a function of mass, we can invert this to determine what the equation of state is, the pressure as a function of density. For binary neutron star systems that you see in Advanced LIGO, this is more difficult because most of the masses in a binary neutron star system are typically around 1.35, 1.4 solar masses, plus or minus maybe 0.1 or 0.2 solar masses. So they're usually found in a very small range of masses. So you could try and parameterize, for example, the tidal parameter, try and force the function for a tidal parameter as a function of mass. But it will turn out that it's actually a lot more useful to measure, to try and parameterize the equation of state and then measure those equation of state parameters. And the reason is because there's already a lot of known information about the equation of state, which I'll describe later, and this allows us to reconstruct the equation of state. So the parameterization that I'm going to use is just a piecewise polytrope. So this is a simple fit to pressure as a function of density. There's in each region you have a polytrope where pressure is proportional to the density to some adiabatic index. So there will be three parameters, gamma 1, gamma 2, and gamma 3, and then a pressure constant at about twice nuclear density. And this is twice nuclear density is roughly the average density of a 1.4 solar mass neutron star. So that's a convenient parameter to use. And what I'm showing you here are the fits for the various these equations of state. So it agrees fairly well, usually a couple percent error. Sometimes the error is larger, but it's a pretty good fit. Okay, so I'll just describe now how you measure the waveform parameters as the first step. So you can do this using Bayes' theorem. So the posterior, which is the calculator given your waveform parameters, given your data stream D, is equal to your prior knowledge of the distribution of waveform parameters. And in this case, our parameters are there's 7 extrinsic parameters, and then we have the 2 masses, and then the 2 tidal parameters. And times the likelihood function, the probability of getting your data stream for a fixed set of waveform parameters. And the likelihood function for stationary Gaussian noise looks like, so can be found from the noise time series distribution. So this is essentially a Gaussian. This inner product here, the is just the integral of the Fourier transforms of A and B divided by the power spectral density of your noise in your detector. So that's how it depends on the noise in the detector. And to get this, to write down the likelihood, we use the fact that the data is equal to the noise plus the gravitational wave signal. And so the noise is just equal to the data minus the gravitational wave signal, which is determined by whatever model you have for your gravitational waveform. And so what you do is you just plug that into this expression to get the likelihood, and then you have your likelihood, and you can calculate the posterior. So what we do is we use Markov chain Monte Carlo sampling to sample this posterior, and then what we want in the end is just the masses and the tidal parameters. So we marginalize over the other parameters just by integrating them out, and this can be done trivially with Markov chain Monte Carlo sampling by just making a histogram of the parameters we care about, which in this case are the 2 masses and the tidal parameter. Okay, so these are the results that we get when we do a parameter estimation for a 3-detector network with the 2 LIGO detectors and the Virgo detector using the final configuration for a signal-to-noise ratio of 20. And the specific MCMC implementation we're using is this loud inference MCMC. This is a very specialized MCMC sampler. What I'm showing you here are the 11 parameters. And the 3 that we care about are the 2 masses, temperature and beta, and then this tidal parameter. And then you can see that this quantity delta lambda tilde, which is the other parameter, is completely unmeasurable. So I'm just zooming in here. You can see that you can measure the chirp mass to about 1 part in 10 to the 4, 10 to the 3. So these are the injected values, and these are the 1, 2, and 3 sigma credible regions. The symmetric mass ratio can typically be measured to a few %. And then the tidal parameter, lambda tilde, can be measured to several tens of % error. So it's not a very good measurement, but the goal is to stack several observations to get a better measurement of the equation of state parameters. So the second step now is to take our n observations that we would get over a long observation period, like a year or 3 years, and then to, instead of measuring the masses and the tidal parameters, try to measure the equation of state parameters and the masses of your n observations. So again, we use Bayes' theorem, and so the parameters that we have are the equation of state parameters, P1, N1, N2, and N3, and then our mass parameters. And there's already a lot of information that's known about the equation of state parameters, and so we'll use that. The 2 ones that are most useful are, the first one is the fact that the equation of state has to be causal. So the fluid in a neutron-star has to have a speed of light that's less than the speed of sound that's less than the speed of light. And so if an equation of state predicts that the speed of sound at any point in a stable neutron star can be greater than the speed of light, then you can rule out that set of equation of state parameters. So what I'm showing you here is the parameter space gamma 2, gamma 3, gamma P1, and this dark gray region is the set of parameters that are ruled out because they predict that the speed of sound, which is square root of p versus d epsilon, where epsilon is the energy density, is greater than the speed of light. So I can rule out those parameters. And then you can also use high mass observations of neutron stars that aren't related to gravitational waves to, again, use as another constraint. So every equation of state predicts a maximum mass for a neutron star. And currently, there are two fairly high mass observations. One is they're both around 2 solar masses, and the lower limit is about 1.93 solar masses. And so if your equation of state predicts a maximum mass below what's actually observed, you can rule out that equation of state. So this is the set of equation of state parameters that are ruled out in this white character. And so the only allowed region in the equation of state space is the part that's not in these two volumes. So that's the information that I'll use as argument known. And it'll turn out this is quite helpful. So then the second part is to use the gravitational wave data. So you can construct a likelihood from just the marginalized posteriors that you got from your n binary neutron star observations. And it's just a product because they're independent observations. And so to get, right now these are functions of the masses and tidal parameters. To get it in terms of the equation of state parameters, you just write lambda tilde as a function of the masses and the equation of state parameters. So you can do that, and then you again have a problem where you want to sample this posterior. There's 4 plus 2n parameters, so 4 equation of state parameters and 2n mass parameters. And so you just want to sample this and marginalize over the 2n mass parameters to get a distribution for your equation of state parameters. So again, we use Markov chain Monte Carlo sampling. The particular one I use is called MC, which works fairly efficiently. And then in the end, you just make a histogram of your equation of state parameters. And then that gives you the final result.
Ben?
Yeah.
So just looking at your previous slide, is it easier to phrase that as a hierarchical model? Because you have these sort of hyperparameters, which are your equation of state parameters, and then you only have to basically compute these marginalizations by summing over the individual posteriors. We can talk about it later, but I think you can probably speed it up a little bit.
Okay, so now I'll just describe the first simulation that we did, which we used as a standard case. So we started with a year worth of simulated data, and for the event rate that we use is roughly 40 events per year for a single detector with a signal-to-noise ratio of greater than 8. And that's roughly a realistic event rate. There's a lot of uncertainty. It could be a couple a year, it could be 100 a year, but probably not. And then for the masses, we used a uniform distribution from 1.2 to 1.6 solar masses, which is also fairly realistic. It might be a little narrower than this, but it's currently unknown what you would actually see in actual gravitational-wave observations. So we started with this distribution, but we also used a couple different ranges. We picked a certain particular equation of state, and then we use that to calculate what the tidal parameter should be. And then we injected that data into simulated noise. For a 3-detector network, using the 2 LIGO and Virgo detector, and using the final configuration. And then we ran through this pipeline to calculate what the equation of state should be. So what I'm showing here is the reconstructed equation of state, the pressure as a function of density, using this year of data. So in black is the equation of state that we started with to generate our binary neutron-star waveform parameters injected into the data, or into the noise. And then to calculate these variable regions, what we do is that each pressure, or at each density, the equation of state parameters in your Markov chain tell you what the pressure should be. So you can make a histogram of each density, and then you calculate what your 1, 2, and 3 sigma intervals are, and then you do that at each density to draw these contours. So the blue is the 1 sigma credible region, the green is the 2 sigma, and the blue is the 3 sigma credible region. And you can see that it does a fairly good job of reproducing the equation of state. On the bottom, what I'm showing you is the error in the estimate. You can see that the error is smallest at about twice nuclear density, where most of the matter in the neutron star is. The errors get larger at higher and lower densities. And there are some features that are equation of state dependent, so that depend on the way it was parameterized. So we use fixed dividing densities here and here. And so what you see is these peaks in the error of the estimate. And so if we had used some other parameterization, such as a polytrope that allows for varying densities or some sort of spectral expansion, these peaks would probably go away. And you can also reconstruct the radius as a function of mass and tidal parameter as a function of mass. So again, we do the same thing where at each mass, these equation of state parameters in your Markov chain tell you what the radius should be for a given mass, and you just make a histogram to then calculate your 1, 2, and 3 sigma intervals. And then you just do that for the whole range of masses, and you get these regions. So again, the red, green, and blue are the 1, 2, and 3 sigma confidence regions. And then again, you can do the same thing for the tidal parameter as a function of mass. And the main thing to point out is the range of masses that we used was 1.2 to 1.6 solar masses. However, because we use these priors and this information about the equation of state such that it's causal, and the maximum mass has to be greater than 1.93 solar masses, and also that the equation of state is inherently monotonic, you get a lot more information. So even at outside this range where the actual neutron stars are simulated, you can measure what the equation of state will be, or what the radius as a function of mass will be. So even at like one solar mass or 2 solar masses, you still get a fairly good estimate. And this is true for the tidal parameter as well. Okay, so we've looked at, we've done a lot of variation in exactly what we choose for the parameters and mass distributions. We looked at what happens if we have higher mass observations. So there's currently a couple claims for higher mass neutron star observations. These are in black widow pulsars. So these are binaries where the neutron star is avoiding matter from its companion and then accreting that matter. And so that's how it can be get up to very high masses. There's two where there's claimed masses around 2.4 solar masses or 2.68 solar masses. But these have very large systematic uncertainties, so it's not really known if you should be trusted. But if you do, for example, measure a 2.4 solar mass neutron star instead of this 2 solar mass neutron star, you can measure the radius to higher accuracy in these higher mass regions, and again, you can measure the tidal parameter to better accuracy for neutron stars with higher masses. We've also looked at what happens if you use different masses in your sample population. So, for example, if we, in our simulated population, if we use only neutron stars that are 1 solar mass, or only 1.4 solar masses, or only 1.8 solar masses, we find that you can still measure the equation of state parameters and the radius as a function of mass fairly well. So, for example, if they're all 1.0 solar masses, you find that the tidal parameter is measured to really high accuracy at one solar mass, which is expected, but because we have these equation of state priors, we can also measure it to higher masses. So this right curve is the population that only had 1 solar mass neutron stars, and then you can see that you can still measure it, the tidal parameter is a function of mass at higher densities and sort of at lower densities. If, for example, it's 1.4 solar masses, well, then that's this green curve. You can see that you can still measure the tidal parameters as a function of mass to fairly high accuracy at other masses as well. And again, you can do the same thing with previous as a function of mass. So we've also looked at several other equations of state, and we find fairly consistent results. So for example, if we, what I showed you was this MPA1 equation of state. If you make your population assuming the S1 equation of state, you can reconstruct that fairly well for the SLY equation of state. Typically, the errors are around plus or minus 1 kilometer in the radius to about 2 sigma. So this is 7 different equations of state being used. And then you can also reconstruct the tidal parameter as a function of mass. These again are 2 sigma regions, and the error is typically around 10% or a few tenths of percent in the year data. Okay, so all of these results assume that we have an exact model for the waveform. However, currently, as I just described, we only know the post-Newtonian waveform to about 3.5 post-Newtonian order. So as a result, if we don't have the correct waveform, then what happens is we get systematic biases in our reconstructed equation of state and tidal parameters. So what I'm showing you here are just the phase differences between various waveform models. So for example, if you use 2 different ways for integrating the energy and luminosity to get the phase as a function of time, what happens is you get a phase difference that can be as big as a few radians over the course of the inspiral from about 30 hertz all the way up to merger at around 1.5 kilohertz. Or if you, for example, if you only use a 3 pm waveform versus the 3.5 pm waveform, you find that you can only measure you find that there's an uncertainty in the phase of the waveform of a few radians. So this means that it's quite likely, because the tidal effect, which I'm showing here for a stiff, medium, and soft equation of state, so this is about as big as the tidal effect. So it's quite likely that you'll get systematic bias in your results because of this uncertainty. So here, what I'm showing you are the results for if you assume that one of these waveform models is the true waveform model, and then you recover with the equation of state or the radius and tidal parameter with a different waveform model for the template. So what I showed before was using this stationary phase approximation waveform, the Taylor F2 waveform, as both the injected waveform and the template waveform. And you don't get systematic biases. However, if you use for example, the time domain waveform, this Taylor T1 waveform, and then try to recover the equation of state parameters or the tidal parameters with the Taylor F2 waveform, then you find a systematic bias of around 2 sigma, or that's as big as the 2 sigma results. So for example, this Taylor T1 waveform is this green region. You can see the bias is as big as an uncertainty from statistical errors. If you use the Taylor T4 waveform, then you underpredict the pressure as a function of density to again about 2 sigma. And you find the same results for the radius as a function of mass and tidal parameter as a function of mass. If you assume that Taylor T1 waveform is the true waveform and recover with the Taylor F2 waveform, then you bias the radius recovered by about 1 or 2 kilometers. Or if you assume the Taylor F2 waveform is a true waveform and recover with the Taylor F2 waveform, then you'll bias the results by minus 2 kilometers. And again, same results for the tidal parameter. That's about 2 sigma difference. So this is a problem. However, these use post-Newtonian waveforms, and they're by no means the most accurate waveforms. So there's currently a lot of work being put into producing more waveforms, or more accurate waveforms. There's several ways to do this. One approach that seems to be fairly successful is the effective one-body approach, where instead of expanding around flat space-time powers of the compactness and the V over C, you use a short-shield solution with a test mass, and then you use the results from post-Newtonian expansions to then deform this metric, and then you can calculate equations of motion. And this turns out to reproduce binary black hole waveforms with a lot higher accuracy. And recently there's been some comparisons where people have compared effective one-body waveforms using tidal interactions to binary neutron-star simulations. And this is, what I'm showing you here are results from Sebastiano, where they used a UV waveform, which is the red curve, and compared it to a binary neutron-star simulation, which is the blue curve. It was matched in this time interval here, and then after that, see that you still get very good agreement up to dot merger. So this is promising. So even if we don't have an exact waveform model from these post-Newtonian expansions, it's possible that either some form of effective one-body approach that might be tuned to numerical simulations, or just numerical simulations on their own, might be able to make a waveform model that's sufficiently accurate so that the equation of state can be recovered with systematic errors that are much smaller than statistical errors. So that was faster than I thought it would be, but so I'll just conclude. So there is in fact a lot of information about the equation of state that you can learn about from binary neutron-star simulations. You can typically measure the equation of state to about a factor of 2, maybe a little less. And the quantities about related to the neutron star, such as the radius or the tidal parameter, can also be measured fairly well. So, for example, the radius can be measured to about plus or minus a kilometer with a year of data, or the tidal parameter to 10% or 0.3%. Now the systematic error is quite large currently using the known post-Newtonian waveforms. But there's ways to improve this, such as effective one-body waveforms, maybe calibrated with numerical simulations, and this will probably make the systematic errors smaller than the statistical errors. Thank you.
So does different for questions?
Sort of curious about the crossing neutron stars enough to cause glitches when they're just like grouping neutron stars. Is there any potential for sleepable gravitational waves?
Not in binary neutron star systems. So it's mainly determined by just the mass distribution of the neutron star. So the cross basically has no effect on the quadrupole moment of the system, and it's basically if there's any like cracking or anything like that in your neutron star, that'll happen well before this region, or before it inspirals, or at 10 to 30 hertz. And so you can essentially just treat it as a perfect fluid. So it probably won't have any effect at all. Rotating neutron stars impact.
So by the time it's observable, these neutron stars are already headed along.
You say that a lot?
By the time the gravitational wave signal is observable, the neutron stars are already headed along.
Not a lot, like in the sense that the rotation matches the orbital period. No, so for that to happen, heating up viscosity in the fluid for the neutron star to basically spin down. Yeah. So that doesn't happen. Just the inspiral is too fast for there to be sufficient time for them to reconstruct a lot. So what happens is the deformation follows a little bit, but the spin doesn't change. So the shape of the orbit will look like this as it rotates, but the matter will still be spinning at whatever initial spin it had.
Okay, because I mean, if you have the spins aren't necessarily the line.
Yeah.
You have some sort of cross. I don't know how much energy would dissipate by constantly deforming.
I think it's much less than the energy radiated from gravitational waves or like the binary.
So, we usually would expect a binary to have a lot of spin, but you could ask the question, you didn't have any spin until it needs to recover. What happens if you put in some measure of spin that you would expect on these constellations, some limitless norm? How would that bias your results? And so you could inject something with spin, recover with non-spin, or you could recover with including spin. And then maybe there's some degeneracy between the tidal deformation counters and spins. I'm not sure what's going to happen.
Yeah, so there's been a couple of papers on the effect of spin. So for example, Markov looked at what happens if you just ignore spin in your waveform models. And there is in fact spin of like 0.05 or something like that. And that biases the results to better, so that the systematic errors are as big as the statistical errors. I know John Lee and a couple other people have looked at, I'll talk about this, and it's
It's very close. It gets you close.
okay. Yeah, so can I talk about it?
No, absolutely.
All right, yeah, so they looked at, they've done a similar analysis, and they've used line spin waveforms. They found that because of this degeneracy that you get between like the spin and the symmetric mass ratio, and then there's also much smaller degeneracy between the spin and the tidal parameter, that increases the statistical error. So you need maybe about, I think, like twice the number of observations to measure equivalent statistical errors. So you do need to include spin. I didn't do that in this paper, but in future papers, I'll have to do that. In the end, we'll want to use precessing spin and everything, because that, as far as I know, breaks some of the degeneracies, but not all of them.
Some of what spins is that?
For what values of spins?
So we typically took the extent of spins. And our distribution, I think, is 0.05.
Is that a ratio? Is that like the dimensional spin parameter?
The
Is that-
ratio spin.
Okay, how close to breakups?
I think the breakup is 0.7.
Yeah, that's not right.
So it's fairly low, but it's, I would say, more astrophysically motivated. But it's a choice that we made in our simulations. And even with that relatively low spin, you see that you do start to need like an order of 2 to 4 more sources to do the same as without spin. So that tells you that each degeneracy is present.
What do calibration errors induced by?
So I didn't look into that in terms of like actually doing a simulation, but so my understanding, at least from, I don't know much about it, but from initial LIGO, the calibration error in the phase is around 0.05 radians or something like that. And that's, it's much smaller than the tidal effects. It's like maybe a few percent, maybe it's not quite 10%. So that will also affect it. I don't know what it will be for Advanced LIGO, but yeah, it's definitely something that will need to be included, but I don't think it'll make the bias the results by a large fraction of the statistical error.
So you do a lot of vector inside
for finding or for measuring the equation state? Did you do any sort of analysis at being able to distinguish between different equational states?
Only in the sense that we, so we didn't do this like model selection type of thing. The one thing we did use, I guess I have another slide. Yeah, so we looked at a large number of equations of state. For example, this is the equation of state I showed in most of the slides. So this is area, and then these other curves are the MPA one equation of state divided by the MPA one equation of state. And you can see that you can usually distinguish between the one we used in simulations and the other equation of state parameters. At around 1 times nuclear density to about 4 times nuclear density. I mean, this isn't in terms of like model selection type thing, but for example, these are the 2 sigma confidence in what the pressure should be, and other equations of state are significantly different from. So, for example, this would be like 5 sigma waveform at this particular density. So, yeah, in that sense, we looked at distinguishing equations of state.
These are all cold equations.
Yes, these are all zero temperature, no entropy or anything.
And people look at cold limit of the hot equations of state.
I know they've done this in simulations of like the post-Newtonian stage of binary neutron-star simulations. I think it affects the frequency by like tens of it, like 10% or something like that, maybe less. For the pre-merger stage where you just have the inspiral, it doesn't heat up significantly at all. So that's essentially different.
Right, but I mean, there's a cold limit of these hot equations of state. It should still be valid. But I guess nobody's looked at this.
Yeah, I mean,
No, the temperature is necessary.
yeah. I mean, I think if I understand, that would just be like another curve in pressure versus density. That is even actually that.
Yeah. Something like this, except with those equations of state.
Yeah, you could definitely do that when you inject those equations of state and try and make it work.
So the inspiral model waveforms that you're using, and I think also the EOB ones from your paper, I think, just looking from the slide, it looks like, of course they're inspiral only, so they're not, they seem to have some kind of cutoff at merger. So when you run your Markov chain, how do you prevent, I mean all the information's at the end, right? So all the information's at the end just before this cutoff in your waveform. So how do you prevent contamination or artifacts from the cutoff?
So it definitely leads to contamination. I know John Lee looked at that. So in the end, what you'll have to do is have an actually accurate waveform model all the way to when the waveform actually cuts off because it merges. So there's this boundary between the inspiral and then the post-merger phase where it actually cuts off to 0 amplitude. So you have to do that modeling correctly and probably do it with numerical simulations.
But when you say do it with numerical simulations, does that mean a numerical simulation that includes matter, for example?
Yeah, so you'll have to have some sort of, sample the parameter space of masses and equation of state parameters or tidal parameters, and then make some sort of surrogate model so that you have an accurate waveform model. So that'll almost certainly have to be done with numerical simulations.
I know this is outside your expertise, but are there people working in that direction? Okay, in the room maybe?
Many.
Yeah, okay.
But actually that is, so with the end model, you need to really cut off the wave.
You need to cut off the waveform in time or frequency?
You need to cut it off.
Okay.
So you don't have any magic. You cannot define any magic.
Right, I understand that, yeah.
And what people do is use the spatial telescope.
Use the
Spatial telescope frequency. Spatial plus development frequency.
Oh, right. Yeah.
So that is brutal, but actually, as an order of magnitude is not bad estimate. It's exactly.
Sure, but my concern is wherever you cut it off.
Yeah.
I mean, if I have some data with a real signal in it, there's not going to be a cutoff in the data. So my concern is if I bring in this template that's cut off anywhere, I have to somehow reconcile it with data. If I bring in this template that's cut off somewhere.
You have to analyze to that. It's not just cutting off the waveform and analyze the high frequencies. You just have to not analyze higher frequency.
Right. So that was my original question for Ben: is how do you do that in practice? And I think the answer he said was it's tricky.
Yeah.
It's a
But that's one of the advantages of using UV. Because UV includes a merger.
it does include the merger.
So the model predicts a merger, but it's thick. And so you have a natural place where you can, but you have a natural merger. Then with and without merger. Because this merger is related to the presence of the equivalent of the stable orbit and the horizon, which is present also in the UV model with mass.
Only tidal effects, but what about all the non-linear stuff that happens at the end?
So what you can do is,
So
if you
here
look
we
at
are talking only about shieldings.
Merger.
Yeah, the merger here is intended as the end of the shield, where it is the end of the shield. And in many, most of the post-Newtonian model, there's no way to tell where the shield ends. Post-Newtonian just diverge at some point, and there's no way to say, okay, here. Whereas in models like UV, actually only one, there is an outlaw end for the shield. And qualitatively, in the analytical level, the waveform follows what we observe in simulations. And so the shield ends, there is maximum amplitude in the time domain, and the shield ends. And so there is, if you want in the this domain, for example, cutting frequency of the spectrum, or the spectra, I would say, the parallel spectrum. And so that's one of the advantages. You're of course getting this part right, maybe, and accurately, of course, the visibility is the tricky part, and that needs multiple interaction. But as a qualitative analytical level, you already include this feature. The trick is actually to make it as qualitative as possible for this kind of analysis, using and injecting extra information from the method.
So do you know how much LSO diverges from the
There's a formula, simple formula that you can use to get this frequency of the peak formula. So you can, in principle, even if you want to use PN, you can take this formula and cut it back. It depends, of course, on the frequency. Defined as this.
You know roughly the radius beforehand. Well, you know roughly the radius of each stop when you suspect that the two objects are touching. That's what it's
That you can like
sure.
And you're still in the linear regime, where you can parameterize it by just the tidal parameter, and not also the.
Maybe if you want to go below this, if you want to look at it as much as possible. So,
But at a certain point, it's no longer just a PM parameter, it's tidal. You go beyond tidal distortion to tidal disruption, and then you get all those resonances, those peaks and these valleys. But you have to stop before that, because nobody has a good model for that yet. But eventually, numerical physics will. Yes.
Okay, so thank you very much, Ben. And there are questions.